Okay, let's talk about fossil fuels. All right, I dug up some numbers. These are numbers from the federal government. They're pretty reliable. So over on the left, I'm going to have resource. It'll be things like coal, oil, natural gas, renewables, so on. And then the percentage of each that we used in different years. I found some numbers from 1976, some numbers from 1988, some numbers from 2012. Now this doesn't exactly show how much energy we use. It just shows during that year, this percentage was from this source, this percentage was from this source. We'll talk about what happened to the total amount of energy through time shortly. Okay, so there's the top three. Oil, natural gas, and coal. Since 2012, I'll have to get some new numbers soon, but I haven't seen any. I can tell you since 2012, natural gas has shot way up and coal has shot way down. And it wasn't the environmentalists that killed coal. Natural gas killed coal. Natural gas can be used just like coal to produce electricity. And natural gas is super cheap right now because there's so much of it. And there's so much of it because of relatively recent advances in an industry called fracking, hydraulic fracturing. That's why we suddenly have so much natural gas. And when you have a lot of something, when the supply is high, the price is low. So companies have said, well, we're going to tweak our machinery to burn natural gas instead of coal. So coal's pretty much dead. It's not coming back. Despite what politicians say, it's not coming back. Simple economics. So take a look at the numbers. What's happened to our use of oil since '76? Dropped a little, about 10%, right? Natural gas had remained about the same. Coal had remained about the same. So if natural gas and coal remains the same, but oil drops, that means something else must be going up. And what's going up are the next categories. Nuclear is more than doubled, almost tripled during that time. And hydroelectric and renewables have doubled during that time. So back in 1976, when I was a kid, we get about 93% of our energy came from fossil fuels, burning stuff from the ground. In 2012 is down to 80-some%. That's still ridiculously high, though. But instead of 7%, now we have 17%. And today it's a bit higher too. It's a little over 20%. I think I saw last it's about 22% nuclear and renewables. But the fact is, we're still a planet that runs on the burning of fossil fuels. The byproducts of burning fossil fuels is carbon dioxide, and we've seen carbon dioxide levels in our atmosphere more than double during my lifetime. And it's definitely affecting the climate in a way that's negative for humans. So here's the bottom line. Fossil fuels, depending on the time, provide humans with 80 to 90% of our energy, but they're not renewable on a human timescale. Now, we can create some of this stuff in the lab, but it's really expensive to do it. We're not good at it. It's inefficient. Far more inefficient than other types of renewables. So this is total energy use. This includes household energy use, business energy use, transportation energy use. What's interesting is that here in the United States, the total amount of energy that we used actually dropped from 1976 to 2012. What's happening to worldwide population during this time? Going up. What's happening to US population during this time? It's flat. So we didn't add any more people really, but we had better and better technology developed during that time. We got more efficient. So we actually use less electricity now than we did back, or less energy now than we did back in the 70s. We don't have substantially more people, and we have really efficient technology. So from that standpoint, we're doing better. Now, if you take transportation out of the equation, driving stuff around, and look at just electricity production alone, these numbers are from 2013. Coal is the big fuel to produce electricity. Go down to Denver, we had these big coal firing plants that would produce electricity. There's some out by Craig, Colorado. You can find these all over the place. A lot of them have switched over now to burning liquefied natural gas, taking gas and squishing it into this high pressure liquid, easy to transport, you can burn it. It burns a little cleaner. But if you look at coal and natural gas, you're looking at 60-some%. And you can see these other forms, nuclear, hydro, wind, bio, geothermal, solar, they become more significant. If we get rid of gasoline burning cars and go to electricity, then you can see that these alternatives are going to be producing a lot of electricity. It's going to be a far more attractive business investment. So every time I see an electric car or a hybrid, it makes me really happy. Even though my family owns an oil company, it's putting my family out of business. But it's going to be better for all of us, definitely. The oil industry, the fossil fuel industry has had it good for so long. Anybody that works in that industry, if they haven't made their money by now, you should not feel sorry for them. Do not feel sorry that these companies are going to go out of business, because they'll be replaced by other companies that will also have really good jobs. All right, let's talk about the background with fossil fuels. Fossil fuels has the word fossil in it for a reason. These are fuels made from dead things. Things died so that you may drive. Millions and millions of things died so that you can drive. You can watch Snoop Dogg on YouTube. Oil. We sometimes call this crude. It has a definition. It's a liquid mixture of naturally occurring hydrocarbons. I can break this definition down. It's a liquid, so it flows in the ground. It's produced naturally. A hydrocarbon is simply a molecule that has hydrogen and carbon bonded together. And these hydrocarbons come from dead plant and animal life. Dead plants and animals. They're not live anymore. So it's liquid dead stuff. It's mostly liquid dead sea stuff. Ocean algae, diatoms, single-celled, multi-celled organisms that live in the ocean, die in the ocean, settle to the muck at the bottom of the ocean, get buried deeper and deeper under more and more muck, heat up, pressurize, and turn into this ooey gooey liquid that we can burn. Natural gas is the same thing, only different. It's just a gaseous mixture. Now, typically when you drill down into the ground and find oil, you're going to find some natural gas as well, and vice versa. They exist together. Some deposits are very heavy on the liquid, get lots of oil. Some deposits are very heavy on the natural gas. Just depends on how old they are, how deep they were buried, what kind of rock they're in. Here in Colorado, we get lots of natural gas. The rocks are the right age, buried the right depth, they're the right kind. That gas forms easily in. Other areas, you go to the Middle East, it's lots of oil, very little natural gas. And then coal is a little bit different. These are basically old swamp environments where you had lots of plant production. The plants live, the plants die, they sink to the bottom of the swamp, they get covered with other plants. Now, something that these all have in common, it's all dead stuff, right? Now, if I died tomorrow and you threw my carcass into the backyard, what's going to happen to it over time? It's going to decompose, right? Yeah, the oxygen and microbes are going to do their thing, and they're going to break me down into all sorts of elements, and ashes to ashes, dust to dust. I'm going to be gone. I'm going to completely decompose. But what happens in these environments is a little different. So you're burying all this plant material under other plant material, sometimes in both cases in water, right? You've got to have oxygen to decompose things. And actually in water, there's some oxygen. That's how fish and other organisms survive, but there's not a lot of it. So when you bury this material at the bottom of the ocean or the bottom of a swamp, there's a little water in there, there's a little oxygen in there, and the material starts to decompose. But really soon, it runs out of oxygen. When the oxygen is gone, then things don't break down as quickly or thoroughly as if you threw me in the backyard and let the air work on me. So it's what we call an anaerobic environment. Anaerobic means without oxygen. So it's a different decomposition process, and it won't break completely down like it would on a land surface, just say. So that's kind of the key, is that it starts to break down, it uses a little bit of oxygen, but then it goes into this anaerobic environment where there's no oxygen present. And remember, what happens as things get buried more deeply? It gets hotter and more pressure. So think of it as an oxygen-free pressure cooker. That's what this dead stuff is going to be in. It's going to be in an oxygen-free pressure cooker. And if you cook it for 1,000,000 years, and that's exactly what's happened in the ground, that stuff turns into oil, natural gas, or in the last case, it could be a solid coal. So here's, again, kind of how it works. And remember, this takes probably at the minimum 2,000,000 years. It can take significantly longer, depending on how quickly it's buried and how hot it gets and what rock type is there. No matter what, it certainly doesn't replenish on a human time scale. So this is for oil and gas. For coal, it would just be, instead of microscopic marine organisms, it would be swampy plants. So out in the ocean, sort of the basis of the food chain out in the ocean, is all this single and multi-celled algae, diatoms. They live their life, they die, they sink to the bottom. Their dead remains accumulate in the sediment at the bottom. As more and more sediment and dead things accumulate, the stuff that was already down there gets buried. And it gets buried deeper and deeper and deeper. 1,000 years, it's buried pretty deep. 10,000 years, it's buried really deep. At first, it decomposes a little with the oxygen in the ocean water, but then the oxygen goes away. The environment is anaerobic. It gets continually hotter over time, more and more pressure over time. This burial continues on for thousands, then tens of thousands, then hundreds of thousands, then millions of years. Like I said before, at first, it starts to decompose with oxygen, but the oxygen is quickly used up. And that oxygen is what's ever dissolved in the ocean water or the swamp water. After that oxygen goes away, you now have this anaerobic pressure cooker environment. And just like if you take eggs and water and flour and yeast and mix it in the right proportions and stick it in the oven and bake it, depending on what ingredients you start with, you might end up with some oil, you could end up with natural gas, or you could end up with coal. So bottom line is oil, coal, natural gas is made by pressure cooking dead stuff without oxygen present. And when you do that, that's what you get: oil, coal, natural gas. And naturally, this takes millions of years. So that's the simple way it works. So you tend to find oil, coal, and natural gas forming in rocks that form from ocean sediments or swamp sediments. So that's what oil and gas geologists do. They run around and they look for rocks that once formed in the ocean that might have a really high organic content. And then they try to find rocks that are about the right age. If it's too young, oil and gas won't have formed yet. If it's too old, what does the oil and gas want to do in the rock once it's formed? Does it want to stay there? Why does it want to move? Oil and gas is less dense than rock, so it wants to move up, and it will. That's one thing. Once oil and gas forms, it starts moving up through the rock, and it'll move all the way to the Earth's surface, unless it gets trapped by a rock that's not permeable. So that's the basis for oil companies. They send geologists to look out for rocks that have the right age, been baked, had organic matter, and then they look above that rock unit to see, is there another rock unit that's not permeable that would trap all this stuff? And then that's where we're going to drill. That's how the whole industry works. Find rocks of the right age that produce the oil, find rocks that are impermeable that'll trap the oil, and then drill down and see if you can get it out profitably. All right, any questions so far? Like I said, oil and gas, once it forms, is just going to come bubbling up to the surface unless something prevents it from rising along the way. So to find oil and natural gas out in the environment in quantities that are profitable, what geologists will first do is try to find a rock that could act as the source of oil. We call it the source rock. Now typically this is a limestone or a shale, because these are the rocks that form from ocean sediments, where all of these dead algae critters can sink and become incorporated in. So again, you want to find a rock that's not too young, so that oil and gas could have formed, that's not so old, so that all stuff got leaked out of it and escaped, or wasn't buried so deeply that the stuff was essentially burned. You know, if you get it too hot and too much pressure, then the oil essentially turns to tar, which isn't really useful for most folks. So you got to find rocks that kind of fall into a narrow range of ages and depths of burial and types. But once you find a source rock, it's like, ooh, I found a rock, it's the right age, buried to the right depth, it's got lots of organic matter in it, oil and gas should have formed, but we know that once it forms, it's going to move up. So then you look at the rocks above it and say, will any of these rocks above it trap it? So you look for something called a trap, which is just an impermeable rock layer, typically a shale unit. We'll talk about shales a lot the last month of class. These are rock units that act as a barrier to movement of gases and fluids. And it's like, okay, here's a trap. So the oil and gas can't rise through it, but then we're going to look at how the trap, we're going to look at the shape of the trap and see, are there places that would be more prone for oil and gas to accumulate than others? And then we're going to go try to convince the farmer or the rancher or whoever owns the land to let us drill there. So if you happen to own land that has the right geologic configuration beneath you, oil companies will send they call them landmen, even if it's a woman. Oil companies haven't become too progressive yet. My sister-in-law is a landman. But what they do is they go out and they talk to the rancher and they try to make a deal with him. They said, you got to let us drill on your property and we're going to give you 1% of the royalties or 2% of the royalties. And it could be this much. They don't tell you it could also be nothing if they don't find it, or price of oil and gas tank or something or other. But they'll say, we're going to make a deal with you. We're going to come to your land, we're going to drill on it, and then we're going to give you a little bit of the profit. And for some people, this is huge. You go up to North Dakota, you've had these ranchers that have had these ranches in their families for over 100 years. They've never made much money because the land isn't all that great for farming or ranching. And suddenly they're getting $60,000 a month. And it's like, I'm not ranching, that's hard work, because I'm just going to go in my mailbox and get my money. I can make more walking to my mailbox than I can in a year of ranching. And that has happened. It's happened out here east of Greeley. It's happened in the Dakotas. And then others, you know, they sign the same deal. It's like, oh, this guy over here is getting $60,000 a month. I'm going to sign a deal, and they get nothing because they don't have the right geologic configuration under their land. So This is kind of an interesting diagram. So it shows how different geologic configurations beneath the earth might trap gas or oil. And the easiest one to understand is this one in the upper left here. Okay, this is a geologic figure called an anticline, or a fold. You can see how the rocks are folded up into an arch shape, right? So let's say that this was the source rock right here. All right, let's say they were able to figure out we have these various units beneath the surface, and this one down here has lots of organics, it's the right age. We think this has oil. The oil's going to rise up. Are there any rocks above it that could trap it? Well, they look above and they see, hey, there's a shale unit right there. That could be our trap. So what they find is that the oil and natural gas will accumulate beneath that trap. What's lighter, gas or oil? The gas. So once this all sort of settles out, the gas rises to the top, then the oil's underneath, and what they're not showing here also is that usually there's water there too. So this, I don't know what that, ignore that, GW might be groundwater, okay? So the thing is that you can't see what's under the surface very well. Geologists use earthquakes moving through the earth to try to paint pictures, but we only know this sort of well. If we had a perfect picture of the underground, that'd be great. What if you drilled right here? Drilled straight down, what would you get? So you go down, 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 down. Oh, I got water. Yay. I got water. And you drill right down here, what do you hit first? Gas, which is sometimes profitable. It's also really explosive and potentially dangerous. This is why people can't smoke on drilling rigs. Things go boom. But think about it. Let's say if your property ended like right there. Let's say this was your property. You've got a neighbor, he's got some oil wells on. They're making tons of money, right? And it's like, I want money too. Come, oil companies, come to my land. Are they going to get anything? No. But they might not know the lay of the underground land as well, and they might think, well, hey, you know, these are producing. I'm just going to go a couple hundred feet. I bet I can produce too, and then they get nothing. And then, you know, the other diagrams you see here show other potential geologic configurations that could trap gas and oil. And these are actually pretty simple. Usually it's way more complex. So if you're a good geologist and can decipher all the geologic data to build the best picture, you're going to be a really sought-after geologist. And you can make ridiculous money in the oil industry doing it. But if you drill a well here for your company and then put one right here for your company, you're probably not going to last very long. So it's a high pressure, high reward sort of field. But that's how the oil, that's the oil industry in a nutshell right there. Find rocks that produce oil, find geologic configurations that trap oil, send your people out to make a deal with the landowner, and then pump the stuff out of the ground. And even if you do find oil, you still might not make any money. It might be really poor quality. There might not be that much of it. So it's a tough industry. But people get better and better at it all the time. All right, let's end there. And I will see you guys all next week.